Okay, yeah, I figure I often get, I'm here, by the way, for the next 3 years. And since there are always these conversations at coffee hour or whatever, I thought it would be useful to give this talk, which is something like a compressed version of undergrad machine learning. So these are the major buzzwords you should be aware of. So when we teach machine learning, so there's supervised learning, unsupervised, and then, as you can imagine, for every concept there's a dozen other variants, which I won't cover, and then the third is reinforcement. Okay, so I'll say a line about each of these. So supervised learning is a prototypical example is you show the machine images of some objects. You know, this is a chair. Show it 100 examples of chairs. Show it 100 examples of forests, trees, dogs, whatever. And then after that, 100,000, whatever. Show it lots of examples, and then it learns to classify. Okay, so recognize those objects. So that's learning from labeled, by which mean humanly labeled data. Okay, and because it's humanly labeled, implicitly we're assuming that there's a sort of small number of labels. Okay, as opposed to a label where the label is, say, a paragraph description, right? You ask humans to label an image by a paragraph of text, right? There's just too many combinatorial possibilities of a paragraph length text. Okay, so that starts getting into the second example. So this is learning from unlabeled data. And it's also very relevant when number of labels, possible labels, is very large. Okay, so therefore in the data that you're given, most labels will not even occur. So that also has a feel of unsupervised learning. And reinforcement learning is, it has to do with repeated decision making. Or sequential decision making, e.g. as in self-driving cars, e.g. game playing and self-driving cars. Self-driving, not just that it can set its own goals and do something. Okay, not just driving as in driving, but also do other things, robots. Okay, so that's a three-way high-level partition that people make, at least at the undergrad level, and so now we'll talk about these. And by the way, yeah, I'm happy to stop at any point for any questions whatsoever. If there are any now, please ask. Okay. So that's the high-order classification, which I'll keep up here. Okay, so the next, which of these moves? This also moves. Okay. So the next one will then be, let's do over here. So this is an example I did in my popular talk. I should probably move this. Does this move? No. It doesn't move. Okay. I was planning to use all of them. How many people? So is this? Yeah. Okay. So here's an example that I did in my popular talk last month, which was classifying text. So, e.g., reviews, Amazon reviews, say. 1 through 5. So you're given the text, and you have to predict the rating. So now clearly, any human, when they look at the text, can see, okay, there are some lines in there, like I loved it, or I liked it, or things like that. So you can imagine that, yeah, by reading just the text, you can predict what the rating will be, right? A human can do it sort of reasonably well. So can a machine learn to do it? So this falls under the supervised paradigm. You're given a bunch of reviews and their ratings. And then you will be given future reviews which don't have a rating, and you have to predict the rating. Okay, it's some kind of a task to check that you understand sort of the overall sentiment of text. So, the way people do it is, and by the way, I forgot to mention that, as I said in my popular talk, all of this machine learning is really curve fitting. If you see it from a distance, and this old idea of Gauss, that you fit curves to data, and there are lots of disciplines on campus, as you know, which have gone to town with it, right? A lot of applied math is curve fitting, right? Econometrics also, right? So this all is in that framework. And so so given that framework, how do you do this? So a text, so there's a vocabulary of size n, let's say. Capital N, that's the number of words in the dictionary, English dictionary. And now reviews are sequences of such words. So assume review has, say, each review has k words. This is, I mean, not all reviews may have the same number of words, but then you can always fill out some zeros or something. And so now a review is really, so third thing, so now you represent review by word counts. How many times did each word appear, each dictionary word? Now most dictionary words will not appear in a review. K is much smaller than n. So most dictionary words will not appear. Review is just a paragraph. So you represent review by word counts. So therefore, that is a very sparse vector. Sparse as in most coordinates are non-zero, 0. Very sparse vector in R to the n. Right? For each word, give me the count. Okay, and now the classifier that you train is basically what's called a regression classifier. Basically, so this is a vector xi. So rating of x is something like summation wi xi minus b. So just a regression function. Okay, and this is a linear. This is a scalar, a real valued scalar, and you round it to the nearest rating. So how do you train this? Whoops. Oh, I see. It doesn't go down. So how do you train this? How do you train this? Just least square regression. You take sum over data, and you're minimizing over w, this vector w, this quantity least square. Summation wi xi, x is data, xi minus b square. Okay, least square regressions. So you find these weights. You can think of these as importance estimates for the words. How important are they for the review, for the sentiment of the review? And then, if you have enough sort of positive sounding words, it'll think it's a positive review. And if there are negative sounding reviews like terrible or so on, then you'll have low reviews. Yeah.
Sorry, the minimum is over b as well?
Minimum is over w and b. Thank you.
Why do you choose this instead of just
You can take many other functions, yes. So yes, it definitely matters. So so this is just a regression classifier. There are others. Again, even you can pass this thing through a nonlinearity. Okay, so this summation wixi is some kind of score, but that score may not transfer linearly to the sorry, minus yi. Thank you. Now I get it. Okay, so there's a rating which is given to you for this thing. You subtract it from here. Okay, so that's why it's being used to predict the rating.
yi is not really I, it's just y.
Oh, sorry, y. Thank you.
Thank you.
X and y. Thank you. Ask a question.
So, like, would you take cubed or just the absolute value?
Oh, yeah, that's what I'm saying. You can do other things here. Like there's logistic regression where you take an exponential, etc., etc.
And they all work.
For this text classification, yes, most of the obvious ideas work. Yeah. Okay, and the reason they work is that in normal text and normal reviews, when people write a review, they have positive sounding words in positive reviews and negative sounding words in negative reviews. So this simple classifier works. Okay, so that's all it is. So this is just curve fitting. By least square regression, you're finding WIs. Okay, so already there are some issues that I want to raise here. So what's the vocabulary size? It could be like a couple 100,000. And k is small, like 50, 100, right? Amazon reviews are not too long. So how many labeled examples do you need to fit this classifier? Well, you're giving a weight to every word, right? So let's say 300,000 or whatever, 200,000 variables. So what would you expect? How many reviews do you need before it can do pretty well?
Most words are not going to show any facts.
Okay. But each word may show up in some review. So question is, do you ignore it or what? Yeah. Okay. So notice that this is just a linear function, right? And remember that if you have d points in general position where d is less than n, then there's always a hyperplane that separates them, right? So so it seems like this fact means that in order to have it, so give me any data point and any labeling, right? Let's say the ratings are just 0 and 1, binary. I can always find a hyperplane that separates them. So it suggests, but doesn't prove, that you need a number of points which is more than the dimension, right? Turns out that's not true. You can train this with 1,000 reviews reasonably well. Okay, certainly with 10,000 you can do very well. So is this point clear? This is just simple curve fitting, right? You want to fit a polynomial. Sorry.
The point is that that's surprising. Why should it be clear? You're just telling us.
Oh, I didn't mean clear. I'm saying is the phenomenon clear? Yeah, or the point clear? Yeah.
The point's clear.
Yeah.
Not why.
Not why. Yeah.
So you're saying that anything in any possible solution is a good solution, or just in practice this phenomenon happens? So if you have an undetermined system, there's lots of potential ways that you could do that will minimize these sum of squares.
Right.
And it could be
That is indeed what I'm saying. There are multiple solutions.
This works fine.
Right.
Or it could be that actually there's some low-dimensional variety or something, and all of these run the same solution space, and they all give basically the same answer.
They don't obviously give the same answer, right? From this point, you can label, like if I have 1,000 reviews, you choose whatever labeling, right? And I'll be able to fit a hyperplane to that.
Sure, but it could be that there's only like 10 good words and 10 bad words.
Right, yeah. So for example,
What you want to find is find the 10 good words and 10 bad words, and really you only have
a 10-dimensional problem. Okay. So there's a more general phenomenon than that, and but generally this question is a very important question, and that's called generalization theory. Okay, and it says that, or it tries to explain the phenomenon. Explain phenomenon where learning works, and I should define this too, with too few or with fewer training data examples than expected. Than the trivial bound. Okay, that's called generalization theory. I won't have really time to go into it today, but it exists. And in this case, the answer has to do, so, and this actually is not very well developed for complicated models like neural nets. People are working on it. But in this case, it's completely understood. And the reason has to do with what's called the margin. So you're trying to find a linear classifier. Let's say it's binary. You're doing a binary classification, good or bad. And you find a classifier which tends to have a large margin. That positively classified points tend to fall pretty far from the boundary, and negatively also pretty far from the boundary on this side. So this is called the margin. And when the margin is high, so that assumes that there exists a classifier, a solution, which has a high margin, then actually some natural algorithms will find it. And in fact, simple gradient descent. And that classifier generalizes. Okay, it works well. Now, works well, I'll also define here, means that performance on training data is approximately the performance at test time. Test data as in unseen data, unseen at the time of training. New data, yeah. Lots of questions, yeah.
But I think in real life, the problem is exactly the opposite, right? Because you have often huge amounts of data.
Yes.
And then the question is, how do you figure out which are the most important characteristics?
That's a different problem. That's a feature learning problem in unsupervised learning. But actually, there isn't a huge amount of labeled data. So because this has to be all labeled by humans. So actually, design of a good data set is actually, some people think, is the most interesting open problem in machine learning. How do you get data sets of millions of examples? And I'll mention a story in a few minutes. Another question, yeah.
This margin phenomenon, how robust is it to having, a couple of points inside the margin, or even not having a linear classifier available?
Okay, yeah. So the margin phenomenon also applies to nonlinear classifiers, and you're allowed to have some outliers in here, or inliers, whatever you call them. Yeah. Yeah.
I want to follow up on this question, White Shirt, about for this Amazon example. Are you just learning 10 good words, 10 bad words, and assigning the weight 0 to all the other ones?
No, it's not quite that easy. Yeah, it has a lot of non-zero words, non-zero weights.
So, is like in practice, the words that aren't important aren't assigned 0 weight? Like ideally, you would like them to be.
Yeah, yeah. You will tend to have a fairly sparse solution. If you have only 1,000 or 10,000 data points, you will tend to have a somewhat sparse solution, but it won't be super sparse like 10. Yeah.
But like words that it never sees in an Amazon review. Does it
Oh, then of course it'll assign 0. Yeah.
Is that of course? I mean.
Well, it depends on the initialization. Yeah. If you initialize to 0. Yeah. Saying that a priori you don't know whether it's positive or negative, initialize to 0, and then. Okay. So let me say more then. Okay, so that's all I'll say about this simple example, which already introduces the basic ideas. Okay, that there's training data, there's labels, you do some curve fitting, that's your classifier, and there's a generalization theory that people which tries to explain how many samples you need. Okay. Now the other important thing is optimization. So this pertains to what's called the sample complexity. So it pertains to that. But so the other complexity we're interested in is computational complexity. And that's the optimization theory. That's the other ingredient. So generalization theory has its roots in notions in statistics. Optimization theory, as the name suggests, is from optimization. And to a first approximation, let's say half the time in machine learning, you use a very simple algorithm, which is gradient descent. Okay, to a first approximation, machine learning uses gradient descent only.
So these are not necessarily quadratic functions.
You can
just gradient of anything
you
might be going. You might have millions of critical points. You don't know where you're going.
correct. Yeah, exactly. So in a more complicated setting, which we'll see in a minute, you may have very complicated functions. They're not even polynomials. Classical math probably didn't even study many of these things, but so long as you have a derivative, you can just keep trying to improve locally and see where you end up. Okay, so yeah, for this simple regression case, this works. So gradient descent works provably and efficiently. For convex functions. So convex as in a function that's like this. And for non-convex, it's an open question, and that's what many people are looking at. So that's a very simple example, which brings us to the complicated example, which everybody has heard about, which is deep learning. It's being used in all kinds of settings, but I will talk about image recognition, the example I mentioned earlier. So you have data, and the data is an image and a label. And the image is of a person or whatever, and label says man or woman, something. So there's data like this. So image recognition is a very fascinating subject, and people have been very intrigued by it. There's a story, apparently true, that one of the founders of AI in the 60s thought vision is sort of this low-level problem, right? The difficult problems is like playing chess, playing Go. Vision is this input-output problem, right? Like a little bit more sophisticated than the keyboard. The camera looks at things, and you figure out what you're looking at. Turns out it's a very difficult problem. He assigned it as a master's thesis. Okay, so the trouble is, this simple examples that people tried is the digits database. So handwritten digits, and you're given a picture, and this is handwritten, whatever, 6 or 7, but then somebody may write it with a dash like this, and so on. So there are many styles, and given some examples like this, you try to predict, given other handwritten digits, what digit they are. And this was already working pretty well. in the 1990s. That was one of the early successes of what I'm going to talk about. But a more complicated example could be what I said earlier, general images and 1,000 labels. So that's a very big data set called ImageNet, which has about 1 million images. And I'll say a little bit more about that. So, so when you have general purpose images, you have things like you may have a bus, which looks something like this, and there are windows and so on. Or you may have a car, which also looks sort of like that and has windows. So, so for us, I draw these scribbles and you know instantly what it is. But yeah, imagine there is a, because it's a low-dimensional thing. But imagine that it's actually pixels, and then at its pixel level data, right? These days, everybody realizes that there's pixels in digital images and so on. So you're given pixel level data also here, and from that you have to sort of figure out, oh, that blob of pixels is a wheel, that blob of pixels is a window, or et cetera, right? It seems that you need to do that, and then there's some kind of a high-level understanding that a bus is something with 4 wheels and some number of windows, but then not all wheels may be visible, so it starts getting complicated, right? So that's why the early pioneers of AI thought that the low-level vision is going to be the easy thing, right? There's no high-level reasoning there, and then it's the high-level reasoning, thinking about geometry or logic, right? That sometimes things can be occluded and all kinds of issues like that, which is sort of the high-level reasoning, which is where AI comes in. So for many years, people were using, so basically all possible ideas you might think of. This is a very sophisticated math audience. If I would ask you to name things, if we don't have time for it, I would even ask you, and I'm sure some of those ideas would come out. So people have tried in the past ideas like wavelets, which is some kind of low-level processing, manifold learning, which was already hinted at earlier, that there's a low-dimensional structure somewhere, Markov random fields, and Gaussian filters, all kinds of things, edge detecting filters, et cetera, et cetera. So, so people had these hand-designed features. So some human designer looked at the problem and said, I'm looking for this kind of feature, and something like this should be good. So these were hand designed, and deep learning was an ambitious effort to bypass that. It's inspired by, as you probably all know, the presumed working of neurons in the brain, although that's still under study. But it's sort of inspired by that. And the idea is to take this linear classifier and just have multi-layer. So this is X now. There's a first layer A1, and now here you compute some sigma, which is a nonlinearity of A1X. Then there's another layer A2. These are matrices. So matrix vector multiplication, A1X, that's a linear classifier, but then you apply nonlinearity, coordinate-wise nonlinearity. And then you apply another transformation, so sigma 2 of A2 of sigma 1, AX, A1X, etc. So you just keep applying these simple transformations layer by layer, and you get the output at the top. Could be 1 bit or 1 number. And just as we had a training criterion here, this is called the loss function. I forgot to say this. This is called loss function. Just a jargon. So you have some kind of a loss function. The output has to match the label or as close as possible. So there's some loss function of X and these parameters A1, A2, so on.
And Y.
And Y, yes, the label. This is the label. Okay, and so now you're just minimizing that again, min over these AIs. sum over x, y in data.
The number of layers is supposed to be small.
Excuse me?
The number of layers.
Number of layers is a good question. So people were hoping to use 3 or 4 originally. And even with 3 or 4, you can do the digit recognition pretty well. Then a big breakthrough in 2012. There's a landmark paper by Hinton et al., which went to 8 layers. And then the people at the company started getting in a race about it, and it went up to about 20-ish, which people, and the problem, I'll say in a second what the problem is, why going to more layers. But anyway, the bottom line is now you have, then people went up to about 100, and now they're talking about 1,000 layers, and they're able to train with 1,000 layers. Okay, this new architecture called ResNet. So there are lots of layers these days. Okay, so how do you train it? As I said, we believe in gradient descent, so you just have this thing. D by dAij loss. Okay, so each edge here has some weight aij. Okay, or at the ith layer is aij. So it has some weight aij, and that's a parameter, and you're going to optimize all those parameters. So you're going to learn these parameters. Sorry? No. AI is a matrix. Oh, you're right. AIJK. Thank you. Yeah. Okay. Yeah.
So none of this loss function involves the nonlinearities. Are those not?
It is. Yeah. So there's some loss function, which expresses this output as an implicit function of all of these. Yeah. So that's why I wrote it like this.
No, I think the question is that there are no parameters that you're learning in the nonlinearity. Like the nonlinearity.
Yeah. For now, assume that's a fixed parameter. You can put a parameter there too. Yeah.
If there are many layers, you would think this would be extremely sensitive to each of them.
Exactly. Yes. So for decades, mathematicians and people like me who study algorithms looked at this and said, this cannot work. Right? As you say, this cannot work, right? Okay, let me first, actually maybe some of the audience may not see. So you calculate this via chain rule, okay? Simple. I forgot to say this. So you can calculate the gradient exactly. There's no problem with calculating the gradient. It's actually efficient. There's a very efficient algorithm using backpropagation, which has been around from the 1970s. It's something like dynamic programming, if you've seen that in elementary algorithms. So instead of a quadratic time algorithm, what you would expect, quadratic in the size of this network, it's actually linear. And that's a big deal, because these networks have millions of parameters. So quadratic would be very large, but linear is fine for today's computers. So this is important, but it's been known for 30, 40 years. Yeah, so going back to your question, yeah, people like us, I mean, I wasn't maybe involved, but yeah, people like me back then were saying this cannot possibly work, right? This hopelessly non-convex problem. To make it worse, yeah, there are more parameters here than the data points as over there. There are just too many optima, not to mention local optima, which can entrap a gradient descent process. So everybody thought this cannot possibly work. So that's actually one of these good scientific stories in this field, kind of like, any of the old paradigm shifts that you all know about, right, in various fields. That this paper really changed the paradigm. Going to 8 layers with a huge number of parameters, millions of parameters, training on 1 million images, that's like really large scale. So this, my student downloaded this data set at some point, and it took him several days on Princeton's fast link, right? So this is really large, because these are, right, each of these is a, yeah.
So backpropagation was already known. What changed in this paper?
Not just, yeah. So, okay, so what changed? So why now? So the biggest thing that changed was the availability of the data set, okay? large data set. So this, I was going to say more about this ImageNet. This was done actually here in Princeton by Fei Li when she was my colleague. And this was about 10 years ago. She realized that there's this new thing called Amazon Turk, right, where you pay people a fraction of a cent to do some little task. So she decided to create, before that the largest data set had 30,000 images. So she tried to make it 30, 40 times bigger than that, and using Mechanical Turk. And she used up her startup grant or whatever to create this, paying Mechanical Turkers fraction of a cent for the label. And it's an intricate problem to correct, because sometimes they're wrong. And so there was some research involved, and she created this. So that's number one. And this was so large that the old methods may not have really been able to really utilize it. Large, but still smaller than number of parameters. Okay, it's large. It takes 5 days to download, even on the Princeton link, but it's still smaller than the number of parameters. Okay. The second thing that changed was the hardware that Avi referred to. So there are these things called graphical processing units, which are the super duper graphical units that are used in computers so that teenagers can play fast video games. And those are now faster than the supercomputers from 10 years ago. They're just massively parallel computers. So these became very cheap, and Hinton's team used this. They were pioneers in this. And these days, this is a big industry to have software that runs on this and make it a nice programming environment. But Hinton's team had to program in very low-level languages, which some of you who know programming would know is a pain, but they did it. OK, and but these days, that's a big industry. All the cloud computing firms are like providing this kind of computational power on the cloud. And the third thing that changed was optimization. So thanks to this thinking about generalization and optimization theory, even though it was largely in the convex domain, which is not the interesting domain here, even though it was in the convex domain, there were these ideas that were developed. So things like regularization strategies.
These are just algorithms to optimize more efficiently?
Yeah. So
Just ordinary
convex optimization, often discovered in the, because if you want to prove a theorem, it was often in the convex case. So you had these regularization strategies, which is something like adding some other term here. It's not a correction term. It's some kind of smoothing term you can think of, which makes this landscape a bit better behaved. And these optimization techniques had a big.
You add that and then take the parameter to 0 afterwards?
Sorry?
You add that kind of thing that changes the landscape, and then take that parameter to
No.
parameter in front end?
There are people who are doing that too. I think you're referring to some kind of a sort of Gibbs sampling kind of cooling kind of simulator. And people have done that too, but this is not doing that. Yeah, it's just other simple regularization strategies which you can add to the optimization, which were discovered in all kinds of other settings. But the point is, everybody who does deep learning knows about this today. And so what that means is that inevitably, you have such a large model. It takes a week to train or several weeks to train. Something goes wrong. You can't just like keep doing it for the rest of your life. You need to have some concrete way to fix things, right? It's a slightly more principled way than random. And this provides that. So these are the three ingredients.
Of the classification of the number of parameters, this idea of convolutions or that you don't
Those existed in the 90s, or even before, yeah. So yeah, since you asked what changed now, so the older things are still relevant. Okay.
What are you saying is partial derivatives are computed once and for all at the beginning?
No. Every step. That's why you need a fast algorithm. Yeah, but see, it's a linear time algorithm, linear in the number of parameters, and it's a few million parameters, which is not a lot for a GPU.
You can compute the partials in parallel, presumably, right? There's no reason to do them one after the other.
No, this algorithm is fairly sequential. I mean, there's some parallelism that you use in GPU. Yeah. So let's not go into that. Yeah. Okay. Any other questions before I move on? So this is deep learning. Do I want to say anything else?
Yes, actually, you didn't say what happens, why this converges when you have several local minima.
Nobody understands. Oh, so nobody understands why this works. Yeah. So both of these questions are open. There's no theorem saying this should work. Now, there's some recent progress. So you can show using gradient descent plus noise, a little bit of jiggle. This is a work of.
When you say work, it works on some set of problems.
Yeah,
right?
you're right. Yeah.
So is the image? Are you still talking about this image issue?
So works as in like provably works. Provably works, right? Nobody knows how to prove that.
I understand, but I'm asking you, clearly this is a subject that's based on people developing algorithms that work. You don't argue with success. I'm asking you, where's the success? On what sort of problem?
What's your definition of work?
Oh, okay. So initially it was image recognition, but now people have.
What does it mean that something is working? I think it's.
Oh, working in the sense that there's label data. You predict label data, labels of unseen data. That's all.
So far it's been working on
that in that sense, yeah. Yeah, you haven't asked a question.
So how important is the choice of sigma?
So the sigma is just ReLU. Okay, so this sigma is just sigma of z is max of 0 and z. So this function, it's a very simple function. So this is z, and this is called the ReLU.
And if
rectify linear.
If I'm attached to polynomials, could I take it to be something like a parabola, or do I really have
You could. People have tried various nonlinearities, and ReLU actually not only is computationally better, but also seems to be better in terms of expressing things. Now, it could be that the computational ease has to do with that. That with the more complicated nonlinearities, the optimization is much harder.
But won't you have to somehow modify ReLU for taking gradient?
Right. So ReLU is, the gradient exists except at this point, and you hope that, in a sort of generic situation, you don't get there. If you get there, you perturb a little bit.
You don't do this to the Fourier transform, or you do it on what side?
There's no Fourier transform. No, just direct calculus. Yeah, no Fourier transform.
No, the sigma, the truncation. You don't truncate the Fourier transform.
No. Just coordinate-wise truncation. Yeah. There might be a shift plus b. Could be like that. Any other questions? Yeah.
But much of this is still in the domain of heuristics, right? Are there any exact mathematical proofs for any?
That's what I said. Both of these are completely open.
But you were about to say
So let me say even something more damning, right? Like more serious, not damning. So for instance, it's known that you can give images from the same data set, give them random labels. Okay? The neural net still can fit the training data. Obviously, for random labels, it won't predict labels in future on unseen data, but the optimization still works. So there's something weird going on. Yeah, so a lot of theorists are engaging with that in the last couple of years especially. Yeah.
And are you somehow looking for low-weight solutions or sparse?
Some of those are included in these regularization strategies, yeah. It's not just sparse, but yeah, there are things like that, yeah. You shape the solution, yeah.
What were you about to say about how when you have a little bit of jiggle, someone's done something?
Oh yeah, so this gradient descent, now we know that gradient descent with a little bit of jiggle can can escape saddle points. Okay, so critical points which are not local minima. So it can escape that. So there's a conjecture also. People have also conjectured that the landscape of these problems is much easier in general, that there are many local minima and they're all pretty good.
Okay,
so things like
what
that.
I was asking is, what are these problems? So it's image recognition is one. This 2012 paper was about images.
Yeah, but there are lots of other things that involve, for instance, images and labeling them with text, or answering questions, translation. I'll go into that. Yeah, sequence-to-sequence models. So yeah, this is there are many other settings too. People have applied this. The conferences are filled with apply this technique to some other domain. Okay, so next thing. Oh, I'm running a little late. It's a 1 hour talk, right?
Yeah.
Oh, okay. So I'll do quickly in 5 minutes each, unsupervised learning and reinforcement learning. Okay, so and what are some examples of unsupervised? What do I want to say? Good. 5 minutes. Okay, so an example of unsupervised learning is language models. Remember, unsupervised learning learns from unlabeled data. So, for instance, it seems quite clear that in order to classify reviews, where you might have rare words, misspelled words, words used in a strange way, somebody has a wrong sense of grammar, there's all kinds of things going on in that. And clearly, if you've trained the machine on just text, Wikipedia text, with no labels, no human labels, or just on novels or newspaper articles, it should have some idea of language, some sense of it, and be able to do better. Okay, so that's the holy grail of unsupervised learning. That it's felt that most of our learning is unsupervised or largely unsupervised, that we are bombarded with stimulus from all sides, and we make sense of it slowly and learn to make sense of it more and more. So that's the holy grail of unsupervised learning. This is still hasn't had as spectacular success as ImageNet, but there are some very good successes here in settings where the number of labels is large. So that's where so the successes are like machine translation, question answering, things like that. So as in presented with a paragraph or two of text, kind of like an SAT style question, and then answer a question on it. So there again, it's still supervised in the sense that the answer is given by a human, so you can train on human answers, but the number of answers is very large, right? Combinatorial possibilities. So it's not like you have seen the answer before. So these are some successes. And so language model, the idea is that you learn to predict next word in the sentence. Okay, and then in learning to do that, you end up learning all kinds of features of text, like parts of speech, some kind of elementary grammar information, some sense information, that some words are similar, synonyms, things like that. You sort of pick it up implicitly in the model. So a very simple example of this is the word-to-vec model. It wasn't the first by any means, but it's so simple that everybody sort of teaches it in a 5-minute presentation like this by Mikolov et al. It was a Google team. Where you say that the probability of a word given the last 5 words is given by the following model. So this will assume that for every word, a vector b sub w in r to the 300. 300 is some kind of arbitrary dimension, but about 300 seems to work well. It could be 500, 1,000. So you're learning these vectors. So that's your unsupervised learning. And you're training according to this model that this is proportional to exponential of VW in a product with the average VWI vector.
How did you put the words in? It's important how you put them in.
Oh, you're just reading text, unlabeled text, and you're trying to predict the next word. Okay?
Asking what the embedding is.
Okay. what's the embedding? So that's what I was going to say next. Yeah. Okay. So this is the model, and the training objective is find VWs that maximize log of the probability of the probability under these VWs to the data. Okay, so you're finding, so given the VWs, you get some probability distribution on data, because given the last 5 words, you get the next word, and you try to maximize the log probability of the data. So this is called the cross entropy objective. And this is the main conceptual idea, just as there's a loss function there, that you try to maximize the log probability of the data. This is an organizing principle of unsupervised learning. So this is some, again, non-convex optimization problem. You solve it. These vectors have very interesting properties. They pick up all kinds of patterns in language, and there is some theory, including some we've developed, for explaining why these end up with these properties.
Are they unit vectors?
They are not unit vectors.
So what does the length end up measuring?
The length ends up measuring, that's an interesting thing, that's one of our theorems in our paper, is the length square is a log of the word probability. Yeah, so we have a paper. I have also, by the way, a blog where I blog about many of these things. I'll put that here before I forget, offconvex.org. Off as in like go off the convex path. So I have some expository articles about many of these things. Okay, any questions?
What's a generative model that you have the theorems for?
So it's this kind of, it's not generative, fully generative, but assuming the first 5 words are known, there's a probability for the next one, and then assuming these 5 are known, you have the probability of the next one. Just that law. So we have, in our paper, we have something like that. It's a random walk on a sphere. So there's some kind of a micro topic which is doing this random walk, and every step it spits out word according to a probability distribution, which is log linear, kind of like this. And then you get the aggregate behavior of this model by integrating out the random walk. And you get some nice theorems, like the one I just mentioned. Like what does the length of the vector correspond to, and so on. So for instance, one intriguing thing which always hooks people is that this has a property that I think Chris Manning mentioned this. So like if you want to solve analogies like king is to, so man is to woman, as king is to, you want to solve this analogy, so you take all these trained vectors, you take v man minus v woman, and now you look for v king, and you look for some word vw such that this is as similar to that as possible. And lo and behold, out of the 100,000 dictionary words, the one that optimizes this is queen. Okay, so by random chance, that could only happen with 1 in 100,000 probability, right? So, but it happens to be queen. And so our paper also explained this phenomenon.
So here equal means like both in magnitude and direction. So like
let me not go into the exact. Yeah, there's some scaling and so on. Yeah. But yeah, you define an objective, and the best one is queen out of 100,000 words. So yeah, I got hooked by this. When I saw that, I said, I mean, linear algebra is emerging out of some crazy non-convex optimization, out of some crazy system, human language. So what the heck is going on? So that really hooked me. So yeah, you can look at some blog posts over here about this. Yeah, the general idea, this is a very simple, you can think of this as some kind of a memory of what you've seen. And now you can imagine that instead of this very simple handcrafted notion of what your memory is, recent memory is, you can have a neural net, okay, that updates that memory. Okay, and that's called that's the model that's used for many of these tasks. Just the buzzword there is a more complicated model. LSTM, long short-term memory, by LSTM, LSTM plus mechanism, plus attention mechanism, etc. So this is actually a very simple neural net, and these are more complicated neural nets. All right, so that leaves us reinforcement learning. And the basic picture here is maybe familiar from, say, game playing. So we call it game playing, where you have a game tree, which is a tree of all evaluations, all possible plays. So this is player 1, who has a certain number of moves. And then player 2 gets a move, and so on, the alternate, right? So that's game playing. So what is the best move for player 1 over here? Well, that's a very complicated inductive calculation, right? So you can write out the entire game tree, and if you have depth k, this may have x of k nodes. And now, assuming you write it all out, you can see what's the, who won after the sequence of 50 moves or whatever that led down here, k moves that led down here. And now, once you evaluate all of that, there's a way to do backwards induction to get the move over here. Okay. So that's a buzzword, backwards induction. So in reinforcement learning, you have something like, imagine a self-driving car. So you have a self-driving car. And it has at every step a state, which is equal to the readings, the vector of readings from the sensors, vector of sensor readings. There's various sensors, and maybe those have been processed by some of these ideas, deep learning and so on. But now you have a reading for whether you're in the middle of the road or side or whatever, who's behind you, who's in front of you. All those readings, it's a vector, or moderate dimension, maybe 1,000 dimension or something. The model, this is important, you model uncertainty by probabilities. There's all kinds of uncertainties. There's your readings may be off, or even the forward model. When you turn the wheel, how much do you actually turn? Depending on the condition of the road, may cause different things. All kinds of uncertainties. You model that by probability. That's a common scientific paradigm in many fields. So therefore, you have some kind of a what's called a Markov decision process. Where you assume that if you're in this state, there's a Markovian assumption that if you make an action A, you go to this other state. So that, let's say you have a probability 3/4, let's say, but with probability 1/4, you may go in this other state. Okay, so that's what I mean. So there's a Markovian process. It's history independent. You're in this state. Everything you know is in this state vector, and there are these transitions. So now your goal is to take actions so that either there's a reward at the end, or just some continuous reward function, like stay away from all other cars. Okay, so you can define a function, my distance to the other cars, or something like that, and that's your reward function. So there's a reward function. So you max the reward function. And the definition of what the optimum reward is exactly along those lines, that you have many possible trajectories, and you have to do a backwards induction. So assuming you know the reward 10 steps away, then you can do backwards induction to compute the reward here. And so that tells you the best action. And so this theory, you know, if you have a Markov decision process that's small, so that you can run in time polynomial in the size of the Markov decision process, that's all very simple to work out. What's difficult is when this decision process is large. It's too large to write, like in this case. Even if this vector is 50-dimensional, it's too large to write, all possible states. And so now this decision process needs to have some implicit representation. And then, like in many other settings, I didn't say computational complexity so far, you know, there's high computational complexity, in this case, p-space completeness. So you can't optimize this in general, but you hope that with real-life MDPs, there's some, you know, some implicit representation. Implicit representation. And which represents, you know, given this vector of state and, you know, what action you should take and so on. So there's some, today, actually, sort of like a neural net, which you train for the states. Given a state, what action to take. Okay, so that's called a policy. So there's a of policy. So that's the technology that underlies reinforcement learning. So that brings me to the end. And as I said, for most of these things, these questions are open and the subject of active work.
Well, thank you very much.